Welcome to Leetcode 968, Binary Tree Cameras. We need to place cameras on nodes so that every node in the tree is monitored. Each camera can monitor itself, its parent node, and its children nodes. Our goal is to find the minimum number of cameras needed. Example 2, minimum 2 cameras needed for this tree. In simple terms, we process the tree from the bottom up. When a node is uncovered, we place a camera at its parent so we cover as many nodes as possible. Each node is either needing a camera, having a camera, or already covered. We only add a camera when a child needs coverage, which keeps the total minimum. The key insight for this problem is to use a greedy bottom-up approach. We traverse the tree from leaves to root, and whenever we find a node that needs monitoring, we place a camera at its parent. This ensures we cover as many nodes as possible with each camera. Each node can be in one of 3 states. State 0 means the node needs a camera because it's uncovered. State 1 means the node has a camera and can monitor itself, its parent, and its children. State 2 means the node is covered by a camera placed at one of its children. Before we start, remember that none or null nodes are a special case. They always return state 2, which means covered. This is because empty nodes don't need monitoring. Let's solve this step by step using post-order traversal. We'll visit each node from bottom to top, and determine its state based on its children's states. Remember, when we encounter a none node, it returns state 2, covered. At node 3, which is a leaf node. Its left child is none, which returns state 2, covered. Its right child is also none, which returns state 2, covered. Since both children return state 2, this leaf node needs a camera, so it returns state 0, needs camera. At node 4, which is a leaf node. Its left child is none, which returns state 2, covered. Its right child is also none, which returns state 2, covered. Since both children return state 2, this leaf node needs a camera, so it returns state 0, needs camera. At node 2, we check its children's states. The left child is node 3, state 0, and the right child is node 4, state 0. Based on these states, node 2 is in state 1, which means has camera. At node 1, we check its children's states. The left child is node 2, state 1, and the right child is none, state 2. Based on these states, node 1 is in state 2, which means covered. We need a minimum of 1 camera to monitor all nodes in this tree. Let's examine some critical edge cases for the binary tree cameras problem. These cases help us understand how the algorithm handles special situations. An empty tree requires 0 cameras since there are no nodes to monitor. For single node, represented by array 1, we need 1 camera. For two nodes, represented by array 1, 2, we need one camera. For skewed tree, represented by array 1, none, 2, none, 3, we need one camera. This case demonstrates an important edge case, when the root node ends up uncovered after processing all its children. Since the root has no parent node, we must check it separately and place a camera if needed. For this tree, represented by array 1, 2, 3, none, none, 4, 5, we need two cameras. This solution uses O of n time complexity, visiting each node exactly once during the postorder traversal. Space complexity is O of h, where h is the height of the tree, due to the recursion stack. In the worst case of a skewed tree, this becomes O of n. Let's walk through the pseudocode for the binary tree camera solution. We initialize a counter to track the number of cameras placed. This is the recursive helper function that determines each node's state. If we reach a null node, we return state 2, meaning it's covered. We recursively check the left child state. We recursively check the right child state. If any child needs a camera, we place a camera at this node. We increment the camera counter. We return state 1, indicating this node has a camera. If any child has a camera, this node is covered. We return state 2, indicating this node is covered. If both children are covered, this node needs a camera. After processing all nodes, we check if the root needs a camera. If the root needs a camera, we place one there. Finally, we return the total number of cameras needed.